Good afternoon. So today we will have another lecture from lecture number 2 from Thermodynamics. So Thermodynamics. And this will be lecture number 2. So we will begin with what's probably known to you. It is phase change. So you know that water, H2O, exists in 3 forms. It can be ice, it can be liquid, and it can be steam or water vapor. So what you know that phase change occurs due to temperature, but also this is affected by pressure. Temperature and pressure. So we can draw a diagram. So here we would have 0, and here would be temperature in Celsius. Here we would have heat in joules. Here we would have 0, here we would have 90. So if we have, let's say, minus 20 degrees here, and if we if we have ice, here we have when water is at -2, it is ice. So we can write that we have ice here. So if we have ice, it means we have solid. So what happens if we heat it? If we heat it, the temperature of ice increases. The temperature of ice increases, so that means that ice warms. It doesn't melt, but it warms. When we reach temperature 0 degrees Celsius, this is 0, we are giving heat, but the temperature of the ice, it doesn't increase, but this heat is used to break the bonds between ice that was warmed to 0 degrees. So this heat is used to break bonds. So here ice melts, we break the bonds, and what happens? It turns to water. So it turns to water, and we have and in this case here we have water after melting. Here we have ice. When we supply some heat again, so here would be supply heat again, the temperature increases. So again, liquid water warms. Maybe we can leave this water, just write it here. Liquid water warms to 100 degrees Celsius. 100 degrees. So this heat was used to increase the temperature. When this temperature increases to 100 degrees, then we supply heat, but nothing happens again. So it means that water boils. Water boils. And again, if we from this part we have steam, and if we increase energy, if we supply more energy, what happens to the steam? The steam also gets hotter than 100 degrees, so warms again. So you see that there are states when we supply heat. So in this state, we only use heat to warm the ice, and when it reaches the critical temperature of 0 Celsius, if it gets more energy, then it turns to water. It melts. If it has more energy, it melts and then turns to water. If it doesn't have energy, if it's not supplied for melting, then it stays as ice. So it means that 0 degrees temperature is transitional temperature. Again then, water warms and boils at 100 degrees. It can turn to steam or not turn to steam if we supply this amount of energy. This amount of energy, it means here, that this, from here to here. So water boils and then steam warms. The process can be written backwards. So it means that basically you need to use energy if you reach the phase change temperature, which is 0 degrees and 100 degrees. You need at this temperature to supply heat for phase change to occur. And at that phase change, the temperature doesn't increase. So that heat is used to break bonds here and to break bonds of liquid water into steam when it boils and turns to steam. So then here bonds, molecules are further away from here than in liquid water, and so they move freely in the volume. So the interactions here are weaker than here, and they became weaker because these molecules got kinetic energy and they started moving by this heat. So the process can be shown to go down. So if we reduce the heat, take the heat away, so what happens is that here we can write that, maybe I will use some different color, so we can write down that this, what happens here, it is that if we take the heat away, it means that steam cools. Here steam condenses to water. Here cools again. If we're taking backwards, here what happens? Water freezes. So you see, 0 degrees temperature is either the ice either melts or water freezes. It's transitional temperature. And here cools if we subtract. So the ice, if we already have ice, we cool it and it reaches minus 20 degrees. So this is the phase change diagram. You have this in concept, so keep it in mind. So here we are considering temperature at atmospheric pressure, but what happens if we change the pressure? If we change the pressure, you know that in the mountains, water boils at lower temperatures. So this is because atmospheric pressure is lower in the mountains. So it means it's and the same thing is that it is more difficult to boil water in a closed container. Why? Because when you boil water in this is closed container. Let's show it's closed. Something. When you boil water in closed container, steam goes up and they are entrapped here. And this steam, these are molecules that move rapidly, have kinetic energy. So these molecules, if they put extra pressure on. When the water is boiling, molecules from here get kinetic energy from heat, and they escape here. So these molecules have more. These are the molecules that escaped from this liquid water. Steam, liquid. So these molecules have escaped. They have more kinetic energy than this, and they are moving here randomly. But what happens? They also move here to this direction, to liquid, and they don't allow for these molecules to escape. So this extra pressure by steam is impeding the other molecules to go to the steam phase, and that's why it's difficult when pressure is increased. That's why it's difficult to boil the liquid water. Another thing, when if you put water into a closed container, and gradually remove pressure. So it means that you gradually remove pressure. So you remove the pressure, take the molecules that were here out. There were molecules, but you take those molecules out. So what's happening? It is that in liquid there are some molecules that some have high velocities, some have low velocity. So there is distribution in velocities, and when there are some molecules here, those molecules that have high velocities, they can't escape here because there is pressure of these molecules. So if this molecule wants to escape here, it gets in contact with this molecule and it is brought back here. So these molecules that are fast cannot escape. But if you reduce the amount of these molecules, so they are taken out, so these molecules fast can escape. So if fast molecules can escape, it means that kinetic energy in liquid water, kinetic energy of molecules of liquid water is decreasing. So this means that if the fastest molecules go away, so this is because fastest go away, and that means that liquid turns to ice at room temperature. So if pressure is decreases, so this occurs at room temperature. So keep in mind that not only temperature affects phase change, but also the pressure. Another thing that I want to talk about is the laws of thermodynamics. The laws of thermodynamics. So we may the first law of thermodynamics so it's written like something we have discussed before. So this is heat, this is the change in internal energy of the system, and this is work. So what is the basic concept of the first law of thermodynamics? It is that the heat supplied, so this is heat supplied to a system can be used to increase internal energy. Internal energy is this of the system, and to do work. So it means internal, if you supply heat, there are molecules in the box. Let's say there are molecules in the box. If you supply heat, gas in the box, if you supply heat, what happens? These molecules, they have, as you remember, U was internal energy was average kinetic energy times number of molecules from previous lecture. So this is average kinetic energy. This is internal energy. So when you supply heat, molecules start to move faster, kinetic energy increases, and that's why internal energy increases. And also, if there is a piston that is able to move, if you supply heat, this piston goes up. This piston goes up. So it means that molecules push the heat supplied here, molecules, they expand, they push this piston up, and that's how they do work. This means that if you provide heat in general, you increase kinetic energy of these molecules, so you increase internal energy, and also some part of this heat and this kinetic energy is used for pushing the piston, and that's how these molecules, they produce work. So it means that heat is turned into change in internal energy and work. And so there is, and as you see, none of this heat is lost somewhere. So another formulation of this law is that energy is conserved. It is not lost, only one forms of energy turn to other forms. So it's neither, so it's neither gained nor lost, just total amount is the same. Yes? So total energy in closed system is constant. It can change to it can change forms only. Yes, if we thought of closed system here, we think of heat is coming from something, so we thought as thinking as closed system here, something where heat comes to this system, okay? Another thing is what we are thinking about is heat engine. Heat engine is a system, a device we thought about the heat engine a bit. We're talking now. We can talk with the laws of thermodynamics, of first law of thermodynamics. So the schematics of heat engine is given like this. It's shown as it is. It's not a mechanical or something. It's just a schematic representation of how engine works in thermodynamics. So heat comes in, and so heat comes in from where does it come? From a high temperature reservoir. From high temperature reservoir, the heat comes in. Here, in this engine turns heat energy to work, so work goes out. And what's going here? The remaining of heat out that did not produce the work. So low temperature reservoir. So some heat comes in, performs work, and the residual heat that did not do work goes out. This is one working cycle, so engine works in cycles. Some heat comes, does work, and that heat that was unable to do work, that is removed. As we talked, yes, in the engine combustion reaction occurs. That's how work is performed, and the combustion products is so heat in comes as let's say fuel goes combustion reaction in the engine, does work, kinetic energy of moving gases CO2 and H2O do work, and the residuals that were unable to residual gases that were unable to do work, they go out. So efficiency of engine, so it is defined as efficiency as work divided by heat taken in. So it means work divided by Qn. So this would be, heat in would be Q in. This would be, heat out would be Q out. And this would be work that was done would be W. This out we may delete, maybe this work. Okay. So here, because engine works in cycles and there is no increase in engines, in ideal case there is no increase in engine's temperature, in ideal case, in thermodynamical case, so we can write as this work is Q in minus Q out. Then this stays, and what happens is, that this is 1 minus Q out Q in. So if this Q out was made 0, then the efficiency of engine would be 1. But as you know, this is impossible to do. This is impossible to convert all the energy to work. So this is about engines. Now what is a heat pump? A heat pump is talking about spontaneous process that happens on itself, that it doesn't need some kind of driving force. So spontaneously heat flows from high temperature object to low temperature object, but never in reversed order. So external work must be done in order to reverse the direction. So in refrigerator, there is electrical energy used to cool the food products, and because in refrigerator heat flows from low energy from low temperature objects to high temperature objects. Yes, inside the refrigerator there is cold, so energy balance is kept that it's lower than outside, so heat is pushed from inside of the refrigerator to outside. So, but spontaneously this doesn't occur, but this needs electrical energy to be applied to reverse spontaneous process. But now we come to the second law of thermodynamics. So, as you see, the first law of thermodynamics is only thinking about energy conservation. It says that heat can be used for increase the internal energy and to do work. But so this is one formulation, and as you know, if you have an object that has T1 that is 100 degrees Celsius, and this is the object T2 100, this would be let's say minus 100 degrees Celsius. So energy would flow from this to this. So heat flows from here to here. Yes, it can occur by radiation, in this case. So heat flows from here to here. Of course, yes. So it tells that, but we know this from practice. But if we didn't know that from practice, what would happen? This equation is not important here, but what would happen? The first law is only the first law of thermodynamics says that what Q goes, let's say Q1 goes from here. Where did it go? It had to go to here. This Q1 comes to here. So it's concerning about energy balance. So what heat leaves, that heat must come here. What energy goes out has to come to sun, because energy is constant. It cannot disappear. Okay? So this law is dealing with energy balance. So if we said that energy goes from Q1 goes from low temperature object to this object, then first law of thermodynamics would be satisfied, because E total is constant. This also says that E total is constant. But this is not important here. It is important that E total is constant. So E total is constant, that's what the first law says. But if all the energy from this body goes to this body, the first law is satisfied. But we know in practice it never happens. So that's why we need the second law of thermodynamics to say whether the process happens spontaneously or no. Spontaneously, always heat goes from high temperature body to low temperature body. This we know. This says the second law of thermodynamics. But this process that heat goes from low temperature body to high temperature body is not against the first law of thermodynamics, but it's against the second law of thermodynamics. You see that in blue or red, energy is conserved. This is in agreement with the first law of thermodynamics, but red is in disagreement with the second law of thermodynamics. So the second law of thermodynamics is talking about whether the process occurs spontaneously. Because there may be some cases different from everyday experience that we may not know. So there are two statements. One is Kelvin's statement. Kelvin's statement is they both exactly say that Kelvin's statement, it is impossible to construct 100% efficient heat engine. Another statement is Clausius' statement. In spontaneous process, heat flows from high temperature body to physical body. Also human body can be temperature high to low temperature body. So these are equivalent statements, and as you see in this statement we have already shown here. So this statement we will show later. So this is second law of thermodynamics. So second law of thermodynamics deals with entropy. So imagine that you have an object. An object has this is T1, this part is T1, this part is in T2. T1 is bigger than T2. So heat would flow from so heat flows to this direction. Heat is Q in this case, Q. So the first body, what happens to the first body? The first body loses energy Q. Let's write it Q1. Q1 should be equal to Q2, yes. So it loses Q1 first, this first object, yes, we can write it first here, second here. This is object, imagine this is metal block, something having one side is T1, another side is T2. T1 is higher than T2, and heat flows from here to here. So first part loses Q1 and it goes to Q2. So Q2 gains this amount of heat that Q1 has lost, but just split in this case for 1 and 2 this amount of Q, and it should be 0, yes, because they are equal. Yes, Q1 is equal to Q2, so this should be equal to 0. But we can divide this thing by temperature. We can divide by temperature. So divide by temperature, but here temperatures are different, so this notation may be not very good here. So let's divide by temperature. Divide by T. So minus Q1 divided by T1 plus Q2 divided by T2. And what happens? Because T1 is higher than T2, so T1 is higher than T2, so this would be, this quantity will be less. Q1 divided by T1, imagine that it is 10 and it is 10 here, divided by T1, let's say it is what? Q1 can be 10, Q2 can be 10, because they're equal. T1 is higher than T2, so T1 is, let's say, 100, this would be 20. So what happens? We write plus and we see what is, it is this, and here it is 0.5, and the result is 0.4. So it means that we have positive value because this is less than this, and also it has minus. So we have positive value here. And we can give, this is not important, and we can give the name Q divided by T to S. So it means that this is minus S1 plus S2 is more than 0. And we can write S2 minus S1 reverse more than 0. You can write delta S is more than 0. So this is called, S is called entropy. Heat divided by temperature is called entropy, and we see that in spontaneous process, entropy increases. Entropy increases in spontaneous process. So entropy is associated by statistical physics that we are not going to analyze here to disorder. to disorder. So it means that if entropy increases, process is spontaneous. So it means if process is going to disorder, to more disorder, it is spontaneous. So spontaneous process always goes to more disorder. We can write this. Spontaneous process so so why cannot we convert why cannot we, Clausius Kelvin statement, why cannot we construct the engine that would be 100% effective? Is that you see, when you have a piston and you have gas here, so the piston is pushed here, but because there are a lot of molecules here, and as we said, in 1 mole there are 10 to the 23rd 1 mole, let's say a lot of molecules here if imagine 1 mole of gas. Of course there's less like in smaller containers because this would take a large volume, but anyway there are a lot of molecules, so it's not likely that because molecules are going to take the state of more disorder, so it's not likely that all of them will push the piston at the same time. So some will push here, some push here, some will push the piston, but some will push to these sides. So this is why this is because system is going to the state of disorder, so that's why it is impossible to make all the molecules push the piston at the same time. So that's why energy is lost here to other directions. So only because this is random, it refers to random energy, and only part of this random energy will do work, efficient work. Yes. So the second law of thermodynamics is a statement of the overwhelming I like the sentence of the overwhelming likelihood of what causes what occurs with systems having large number of particles. So it means that spontaneous process takes the state or goes to the state, goes by itself to the state that has the most likelihood, it means is the most probable. That means has the highest probability. Has the highest probability. So if you say let's say you have ping pong balls in a box, so they are organized like this. They are just like this, and you shake the box. So what happens? You find them. Let's say you shake, and what do you find? You find that maybe they have changed their position somewhere. Maybe some more clustered to the right side. Okay, you just have shaken, but you will never find them positioned like this. You see? Although it is possible, but not probable. Very unlikely this occurs. For this to occur, we would need to wait for a lifetime of more than the lifetime of the universe to occur. So it is possible but not probable. Probability is practically zero. So because this state is associated to low, extremely low entropy. Low entropy. No disorder here, order, total order. So this is impossible to occur. And if you say there is some kind of distribution, that's that same Maxwell that we talked about electromagnetic, so a bit talked about electromagnetic waves, and we will talk later. But there are some distributions in thermodynamics that say that distribution like this, it shows that this is the probability. The integral of this curve is 1. It means that the sum of all these probabilities is 1. So this is the state probably, let's say, number one state that would never occur. That it means that it's associated with ping pong balls having this arrangement with total order. So probability practically is 0 here. Then this some kind of state number 2 that has let's say where it is. State number 2 would be somewhere here, that more probable. State number 3 this is the most probable. This is some kind of state number 4. The most probable, let's call it probable. This probable, this is not probable. Here would be state 4. This would be state 5. State 5. not probable also. So what happens here? We see we have state number 1, total order, total this would be total disorder, total disorder, total disorder. This was total disorder. This state is probable states, some degree of order. This is most probable state, and this state is probable, some state of order. This state is not probable, and this would be total order. This would be total order. This would be total disorder. So in this total order, if we say that here is entropy, so this would be total order. It means that balls are standing here. As I said, balls here would be standing in this case in total order. Sorry again, I'm disturbing. So this would be disorder. Sorry, I was good. Total disorder. Total disorder here because entropy increases in this direction, and this would be total order. I was correct that time, sorry. This would be total order. Total order, okay? Total order here, less entropy. This would be total disorder, a lot of entropy. This is probable state between some kind of a bit entropy is increased here. This has more entropy. This has the most entropy. This has even more entropy because entropy goes here, and this has the most amount of entropy. And you imagine, as I said previously, this part of very order arrangement, now not confusing, this part of order arrangement would be total order here, but it's not probable. It's not probable because probability you see is 0, but would be less entropy, the least entropy because an entropy here is 0. Here these are intermediate states that can occur. This curve may have some kind of shape like this. It can have the shape like this or something, but and when we see that this is some kind of state where it's less order. This is even less order here. This is here it is more disorder, and here it is total disorder. It means that here this also never occurs, this total disorder, because here, let's say in total disorder, what would happen? The balls would, if you shake the box with the balls would go into pieces, and this would be total disorder, but this also never happens. So that's why this has also zero probability, zero chance. So they never arrange like this, where is total order here, and they never go into some kind of pieces, into halves, let's say. So this would be here. So the most chances to get the state and to get the arrangement of the balls is here. So this is what I was saying wanted to show what the entropy means. Some other possible systems may have this kind of shape, where the most probable state is here. Others may have this one. So this is what I wanted to illustrate for you. So this would be all, and thank you for listening from Thermodynamics.